Okay, so for 7.8, we're going to be comparing what are called growth rates. And in order to get an idea of what I mean by that, we'll have to look at graphs of several functions and compare what they look like. So I'm going to switch over to my graphing tool here. This is the wrong tab. This is the one we need. It's just open to the wrong window or the wrong tab. Okay, so here's my graphing tool, and the three functions that I want to compare are the ones on the note sheet there. I want to look at the natural log of x. So this is a function that we've met recently. It's not a very steep one. And let's compare it to a more familiar function, y equals x squared. Maybe we'll zoom out a little bit. And let's just chop this a little bit. Let's just say x should be greater than or equal to 0. So comparing these two graphs, we can see that even though both of them are growing, and in fact their limits are going to be infinity if we checked, that the x squared function is growing much faster than the log x function. And we know some other functions. Let's zoom back in. Another function that we met recently is the natural exponential function, this guy. And when we're zoomed in this far, it looks fairly similar to the x squared function. And also chop that one at 0. But if we start zooming out, and more specifically, if I start changing the y range, we can start to see how the exponential function is going to start growing faster. It's getting higher faster than the x squared. And let's step back again, maybe to 100. So you can see how this one's much higher than the corresponding x squared function. Let's add another 0. Here the difference is even more apparent. The log function in red looks almost totally flat. The x squared looks like a steady curve upwards, and then the exponential function looks like it's going almost vertical. So when we've zoomed out about this far, we can really get an appreciation of the fact that the exponential function is growing much faster than our polynomial x squared, and that in turn is growing much faster than the natural log function here in red, which is almost totally flat. So what we're going to discuss in this section is a more rigorous, mathematically rigorous way of comparing these growth rates using limits. So well, first of all, do you have any questions before I get rid of the graphing tool? No? Okay. So let's keep on going. We saw in the graph that all three functions grow to infinity as x grows to infinity, but they do so at very different rates. So maybe just fill that in on your notes. Okay, and next, like I said, we're going to use limits to give a more rigorous definition of our comparison. So what we're going to do is start with two functions, f and g, and they're going to be functions that are eventually positive. maybe I should explain what I mean by that. What I mean is that if we plug in large enough values of x, eventually the function is always going to be positive. So if I go back to my graphing tool, I can graph a function like y equals x to the third power minus some large number, let's say 50. So this purple curve that I just graphed in, we can see that it starts out as a negative value. But then if our x value gets large enough, if what we're plugging in gets large enough, eventually the function is always going to be positive. It's going to look like this one here. So does that make sense? No one's arguing. So here's our limit definition. We say that f grows faster than g. And